So like I said, we're going to cover several things today. The first thing is not a major thing. The first thing is a how-to that we're going to use for the later stuff. So imagine, if you will, so picture, we have a surface. Actually, I'll use two different colors here. The usual way I like to do this. I have a surface. Now, we know how to find the surface area. We did all that stuff before, right? So we said, well, let's take a piece of this, and then when we project it onto the xy plane, right, we get something down here. Where that is delta xi, and that's delta yj. So this area would be area ij, which would just be the product of those two things. And we said this piece here, excuse me, this piece here, we said the area was delta sij. Remember, this was the surface piece, right? The sequence, if you will. So that, right, we projected down, and then we were able to find the surface area from that. I'm not going to rederive that. We know. So if I wanted area, so in formal terms, area is the double integral over the surface of this. That's exactly what it is. We can't integrate that, so what we did was we said, well, if I do it as the double integral over the region in the xy plane, then what was the multiplier that we needed? The multiplier that we needed, if you remember, was this quantity. And then I could integrate dA. And you guys got very good at that, and that was actually on your last exam, I believe. Is that right? Or have we done this exam yet? No, actually, that's the first thing. Never mind. It's one of the first things on this next exam. Sorry. So this is something that we did not struggle with. Great. Now, I'm going to throw a curve at you. What if at every point on this surface we had a different density? So I've got a surface. Think of this as being a thing, not a volume. I have a surface. So the surface is paper thin, literally, but at every point on this surface I have a different density. I want the mass of this surface. Does that seem like a reasonable request? Find the mass of something? Yeah, because I know density figures in. But how does that figure into the integral? Well, then if we break it up, I would multiply every one of these little areas by the density, which in this case would be mass per unit area. Then we do the Riemann sum and add it up. But in the end, what does it come out to be? It comes out to be, in the end, whatever that density is would go right here. Let's call that density G of XYZ, for lack of a better name. Now, that can be complicated. It can be very simple. That's not really the issue. Okay? Everybody cool with that? Now, let me go back to my surface. If I define my surface as z equals f of xy, which is the usual way we define it. Remember, we could say the floor is the xz plane. We could say the floor is the yz plane. That actually doesn't matter in real life. You would orient it however you chose to. All of you would generally choose to make floor and ceiling this way, because mentally it's just easier to picture. But you know, from a mathematical standpoint, it doesn't make any difference whatsoever. If I wanted to find the volume of this room, I could make this the floor, that the ceiling, and we'd get the same number. I have a small problem with this statement here. Can anybody tell me what it is? Anybody see a small issue there? What do you think, Bowden? Well, I have a double integral, but I have three variables. You see, is that a problem? Yeah, it's not possible. Not if I want to get a scalar answer. I could get a functional answer. So how do I fix that? Right here. If z is a function of x and y, then all I need to do to fix this is to make this g of x, y, f of x, y. Oh, okay. Now what do? Now I replace the ds with this and integrate over the region in the xy plane. So at this point, this would simply become the region in the xy plane of g of x, y, f of x comma y, then the square root of fx squared plus fy squared plus 1 dA. That's it. So it's basically the conversion of this particular integral into this. So we already know how to find surface area. That's not a new thing. But now what if I want to integrate something over the surface? And the simplest example would be to find the mass of something. So I'm giving you something with a variable density. So, excuse me, let's do a simple example of this, okay? I want to integrate, let's say, z cubed ds, where s is the portion of the cone, z equals the square root of x squared plus y squared. Now, if it's z squared equals x squared plus y squared, it's both top and bottom cone. When it's z equals square root, remember, it's just the top part of the cone. We've done this. Between z equals 0 and z equals 3. So what that looks like, quite simply, z equals 0 would be the xy plane, right? We'll call that z equal 3. Everybody got it? So I'm bounded between the xy plane and here, so I only have this small portion of the cone. I'm integrating over its surface, not over its volume. Okay? So this makes it really simple. You just purchased an empty ice cream cone. Okay? An empty ice cream cone. There's nothing in it, but the cone itself, do you agree the cone itself has mass? But the cone itself is very, very thin, so I don't think of the thickness as really being a part of the thing. I have the ice cream cone itself, and I'd like to know what is the mass of the cone. And let's suppose that the batter used to make it, you didn't mix around very well. It's very lumpy and stuff. So in other words, it's not uniform density. It's more dense in one area than another. Then if I said, how do I find the mass of this cone? Basically, you're doing this kind of a triple integral. Except that you would have probably a different density function. So in this one here, I have a cone that gets really dense as you go up. It's way denser at the top than it is at the bottom. Okay? So I want to do this. So how do I do this? Well, I'm going to replace z cubed, obviously, with the cube of this. This is my surface. This is my f of xy, if you will. So I need fx and fy. So fx would be, if I think of this as x squared plus y squared to the 1/2, then this is 1/2 x squared plus y squared to the -half times 2x, which is simply x over the square root of x squared plus y squared. Then what's fy? Well, we can be lazy here. It's going to look the same, isn't it? It's going to be y over the square root of x squared plus y squared. And finally, what is fx squared plus fy squared plus 1? Well, it's going to be this squared plus the other guy squared. Oh dear. Oh, here we go. Plus 1. Okay, all under the root. Can I do anything with that? Well, first of all, x squared over x squared plus y squared over x squared plus y squared. Isn't this right here just equal to 1? You have x squared plus y squared over x squared plus y squared. Okay, so this is just equal to 1 plus 1 or root 2. Ooh. So therefore, I can say that ds is root 2 dA. Because remember, ds is this quantity dA. Well, that sure makes my integral a little bit easier to state. So now we can say, I'll restate it over here, the double integral over the surface of z cubed ds is the double integral over the region in the xy plane of this quantity cubed. Okay, never like to hear that sound. So we have x squared plus y squared to the 1/2 cubed, so obviously to the 3/2. then times root 2 dA. Now, difficult? Easy? Ooh, what is my region in the xy plane? When you're standing on top of the z-axis and looking down, what do you see? Circle. Which circle? The one on top? You see the top circle, exactly. What is the top circle? If z equals 3, then my top circle is what? 3 equals the square root of x squared plus y squared, or x squared plus y squared equals 9. That's what you see. That is the region that's projected into the xy plane. Well, clearly, between the integrand and the region, we're going to go polar. Agreed? So if we go polar, what does this become? Well, that's r squared to the 3/2 r dr d theta. Obviously, theta is going 0 to 2 pi. What is r going from? 0 to 3. Yeah, 0 to 3, because 3 equals the square root part. Remember, the square root of x squared plus y squared, that is r. So basically, you're going from r equals 0 to r equals 3 without realizing it. That's what that says right there. So when I clean this up, that would be 0 to 2 pi, 0 to 3, r to the 4th power, you already theta? So that would be, oh, and I'm sorry, don't forget the root 2. I'm going to put the root 2 in front. Get it out of the way. All right. So now that gives us root 2 over 5, if you will. R to the 5th from 0 to 3 d theta. Okay. Well, this is coming out really nice because that's just going to be root 2 over 5, 0 to 2 pi of 243 d theta. I'm integrating a constant over constant limits. So my final answer is going to be what? 486 root 2 over pi over 5 pi. I mean, kind of ugly, but again, I had circular region, but not terrible. Okay, so what would this represent? This would represent essentially the mass of the ice cream cone that I just had, okay, given that density. Do I have to worry about units in this case? No, because none were given in the problem, but realistically, what kind of units would G be, do you think? Think about that. You integrated over the area, and your answer was probably mass. Well, if you're integrating over the area, that means you're multiplying by area, and you're getting mass, so...
The density.
Yeah, but what is it? What are the units then of G? The hint, if you're taking something, multiplying it by area, and getting mass.
Mass over area.
Mass over area, good. So your density G is mass per unit area. I'd mentioned that before, but what's odd about that is it's a function of x, y, and z. But remember, we're on the surface of something. There's no volume associated with this problem. That's the tricky thing. When you're on the surface of something, you're on the surface. You're not talking about the inside. That's where it can be a little bit confusing. If I had a solid object, oh, now we would do the center of mass problem, and those would be triple integrals, wouldn't they? That's a very, very different problem because that's mass of a solid. All right, so this is just an exercise in figuring out how to evaluate a surface integral. That's what we just did. That's it. In and of itself, this doesn't really have much use for us by itself. It's what we're going to use now to help us do the next thing. And the next thing is, well, really a big thing, okay? So, new problem, same picture. All right. The easiest way to interpret this one is, I like to use the river example. I have a rushing river. I want to create a dam, but I don't want my dam to be a physical structure. I want my dam to be something porous, like a big sheet. I take a big sheet and I go from one end of the river, or I should say from one side of the river to the other side of the river, and I have the sheet, you know, completely blocking the river. Well, is it going to block the river? No, the water's going to flow through the sheet. But how does it flow through the sheet? As it hits the sheet, it's going to squirt in every which direction. Okay, you got that? So I have something that's porous where the water can actually pass through it. And what I want to measure is the actual flow of the water. Literally, how much water is passing through per unit area. Okay, does that make sense? So that, by the way, this is actually done with rivers, just to figure out what's the flow of the river. If I want to dam up the river to, do an electrical situation, right, get the turbines going, well, I kind of need to know what is the flow of the river. But it's not a force that I'm looking for. It's actual quantity. How much water is passing per unit area. Now, why per unit area? Because if, let's say the river is flowing this way, and this is my big sheet, this wall right here. It's the area of the wall that I care about. Not the volume of the river, but the area of the wall. So how much water is going through per unit area? So think about that. I have a lot of water flowing through. Well, if the trickle is small, then there's not a lot of water. If it's rushing, there's a lot of water per unit area. Okay, that term flow, it's a form of flow, but there's another word we're going to use. So the idea is I have a small section that I'm looking at, and let's say the water is squirting, this way with a certain force. Okay, so as the water squirting through, some of the water might be going that way, some of the water is going that way. Does everybody understand? The water's pointing in every which direction. Is all of the water perpendicular to my horizontal surface? No. So consider that right here is the unit normal. Let's say that vector is perfectly normal to the surface. So if I want to know how much water is flowing out, it's easiest to say how much water is flowing out in the normal direction. Well, how do you do that? How do I determine how much of this is in this direction? Any ideas? We should know this one. We've done this one. I'm pushing the refrigerator across the room. How much do I get done in this direction? What do we do? I'll give you a hint. What do we do?
Dot product.
Dot product, good. Yeah, that was my subtle hint. My dot. I do a dot product. Oh, okay. Well, that makes it easy. So what I want to do is take F and dot it with N. Okay. That tells me how much force is going in that direction. Okay, you with me so far? Now, what do I want to do with this? I want to integrate this over the entire surface. Now, how do I do that? How do I integrate this over the entire surface? Well, first let me write it like this. How the heck do I do this? Well, we just did this. This is a scalar valued function. Agreed? I say it's a scalar valued function. It's not necessarily a scalar. In fact, it's almost certainly not going to be a scalar. It's going to be a function of x, y, and z. So when I get done with that dot product, what will this integral look like? This one. Now, my answer is not mass. No, but the form of the integral will be I'm integrating something here with x, y's, and z's in it over a surface. So the integration that I'm actually going to perform is going to look like that one. So then I'm going to do all of this stuff and I'm going to change it. Are you with me? F is given. N is not. But what is given? What is given is z as a function of x, y will be my surface, just like before. And clearly I'm going to have a region in the xy plane. That's not the issue. I'm not going to give you n. How do I... Anybody got any ideas? Do we know something that looks like the unit normal to the surface? Or at least points in the same direction?
The gradient.
The gradient. Oh yes, we know the gradient vector points in the same direction as the unit normal, but is the gradient a unit vector? No. So therefore, what is n? N is the gradient of 1 over the magnitude of the gradient of something times the gradient of something. But I don't have a gradient yet. I need a 3-dimensional gradient because my force is 3-dimensional. How do I get a 3-dimensional? We've done this one before. I know we had a week off, but I need to create a new function. Let's call it, I don't know, g of x, y, z. And what will it be?
G of x, y, that's what.
It's going to be f of x, y minus z or what? Z minus f of x, y. It's one of those two. This is how we create a function of three variables. We've done this before. How do I know which one it is? This is actually the easiest part of the problem. Which way is your normal pointing? If my normal is actually pointing up, in my picture my normal is pointing up, then which subtraction do I want? The first or the second?
First one.
Think about that. Because the gradient is going to be the partial derivatives. So the gradient with respect to, when I do the derivative with respect to z, it's either going to be a negative one or it's going to be a positive one. So if my normal is pointing this way, then I need the z part to be positive one. If my normal is pointing this way, I need it to be negative one. This is actually the simplest part of most problems. Which way is your normal pointing? If I said, let's consider a sphere, isn't everything in the upper hemisphere going to have upwards pointing normals and everything in the lower hemisphere downward pointing normals? Yeah. If I had a paraboloid, think of the different shapes that we've worked with. You already know which way the normal vectors are pointing. So in my picture, the normal is pointing upwards. So we would choose this one. If my normal was pointing downwards, like the bottom half of a hemisphere, then I would pick the other way. And the reason is, if I choose the wrong one, my final answer will be off by a factor of -1. And that actually does matter. It'd be like saying you have the flow of the river in the opposite direction. That actually can make a huge difference in your calculation. So this is going to be G, where I've defined G. Okay? Now, it's not life or death if you have it pointing in the wrong direction, because in the end of the problem, you'll know by the magnitude of your answer, or I should say the sign of your answer. So, I got this thing here. Boy, that makes it a heck of a lot easier. So now, that means this will be the double integral over the region in the xy plane of f dotted with 1 over the magnitude of the gradient times gradient. And then I'm going to multiply that by fx squared plus fy squared plus 1 dA. Ah, that's a lot of stuff. You know, what's the magnitude of the gradient vector? If this is my gradient, excuse me, if this is my g, then what would my gradient vector be? Wouldn't it be negative fx, negative fy, positive 1? Now, if I chose the other, it would be positive, positive, negative. And that's why, in the end, it will make a difference of your sign if you do the wrong one. But why is this kind of nice? Because what's the magnitude of my gradient vector? I did everything right. Won't the magnitude be fx squared plus fy squared plus 1? Why is that a good thing? Because if I did everything right, what's going to happen to those quantities? They're going to cancel. Ooh. So can't I just skip that step? No. Because you find these completely independent of each other, and you could actually get different answers if you don't do it correctly. Now, you find them independent of each other, and then hopefully you got the same thing if you did it right. That's kind of how it works. So you never really are going to multiply these things out. You're going to set it up and cancel. But people say, well, I'll just skip that step and go to the next one, and usually they get the wrong answer as a result. Half the time they have the wrong sign, and the other half the time they didn't do the right gradient to begin with. No, you don't cancel them before you start the problem. You do the problem, you calculate them, and then when you set it up, they should cancel every time because you set it up correctly. Well, can't I just do one and not the other? What's the danger in doing one and not the other and canceling them? Because the one you did might not have been correct. You're finding these independent of each other. You're finding them differently, but you have to get the same thing if you did it right. That's how you know. It's like the easiest check there is. Now, what about if I pick the other one? It matters with the gradient vector. It doesn't matter with the magnitude because you're squaring everything. So the negative signs don't show up here. They show up here. That's why you actually need to do this, because you've got to make sure your signs are correct. Okay, everybody cool with that? So we're going to do something now. What is this? Well, this is considered kind of important. I'll give you a hint. Most Americans' first exposure to this was back in 1985. Yeah, there was a very classic movie where Michael J. Fox and I can't remember the crazy old man and the DeLorean time machine. How many have seen that movie? It's based on pure physics and pure truth. And what was the key component to be able to do the time travel? You guys remember?
Flux capacitor.
The flux capacitor. Folks, this is flux. Yeah, after today, you guys will be able to travel through time. At least I think so. Yeah, this is called flux. Now, what was another name I just said this can be called? Same first two letters? Flow. Flux and flow are the exact same thing in this context. The difference is we often use the term flow in a different capacity. We often use the term flow in a two-dimensional situation where I'm just talking about water running, in a particular direction, but I don't think of it as a three-dimensional problem. I just think of it, if the river's going that way, we don't think of this as three-dimensional often. So you say, well, how can it be two-dimensional? Well, because it's moving on a curve, horizontally. Flow is often the result of the line integrals you just did. So the work problems you just did, some of those integrals are referred to as flow. I said, generally speaking, we're always coming up with work. Okay? Think of the units of work, right? Energy and work are the same units. But if I change the context and say, no, now I want flow, now I want volume of water. I think water, it's easier. I want volume of water per unit area. So flow is different. If I've got water rushing down the stream, I say how much work or how much energy is created by the water moving. But I could also ask, what's the flow of the water? How much water per unit energy, or per unit area, is actually going? You see it, same situation, different context. So the units in those answers would be not the same thing. So if it's a flow problem, it's not work units. It's volume per unit area. If it's a work problem, we already know what work units are, and you would know ahead of time. Everybody okay with that? So this is called flux. This is considered one of the more important results from this class. And it's really complicated at first, but more often than not, you get an integration that's not that terrible. It depends more on how complicated the force vector is. So let's do an example or two, shall we? So a question can be posed in many ways. Sometimes the question is simply find the flux. Sometimes it's evaluate the integral. Let's see, I got an example here. Start with a simple one. So we're going to do the following problem. I'm going to ask the question without using the word flux. This integral is the flux. So sometimes it's evaluate this integral. F is 4y, 6, 2z, and S is the portion in the first octant. We know that is a plane. So what I have is a plane that's cutting this way through the first octant. So my surface is this. My surface are not the x, y, x, z, and y, z planes. My surface only has to do with this. So this is infinite, but it's being cut off by the three planes. Everybody got it? So it's this technically triangular shape. You with me on that one? So it's not a complicated thing to consider. Might not be a bad idea to draw it. You never have to draw it, but a lot of times it makes it much simpler to interpret. So I'm going 6 in the x direction, 3 in the y direction, and 24 in the z direction. So it's this surface right here. Now, which way is the normal pointing? It's harder to see on my picture, so let me make it simple. Here's my plane. My plane is cutting through this way. Okay? It's angled this way. So what direction is my normal pointing? The marker's the normal. The normal is pointing this way. Is this pointing above the xy plane or below the xy plane?
Above.
Above. Therefore, am I going to go z minus function or function minus z?
Z.
Z minus function. Okay? So I need to define, okay, so z, which was going to be my f of xy, is going to be 24 minus 4x minus 8y. Everybody okay with that? So I'm going to now let g of x, y, z. Now, why do I have two different things? Because this guy right here, the f of x, y, shows up in my surface area parameter. That's what this is called, the surface area parameter. It's going to show up when I replace ds with stuff dA. That's where f of x, y shows up. Why do I have to redefine this? Because that has to do with the normal vector. There are different things going on here. There's no vector here. This is unrelated to a vector. This only has to do with the projection of my surface onto the xy plane. That's what this is. It's the multiplier I need to make this, the area of the thing in the xy plane equal to the area of the thing that's being projected. Nothing related to a vector in any way. This is a vector that I created to get a normal vector. Does that make sense? They're completely separate entities, but I'm using the same original function. So with this, the gradient of g is then what? Oh, I haven't finished this. So if it's going to be z minus, then everything's going to go back on the other side. So in the end of it, it's going to be this. 4x plus 8y plus z minus 24. Oh my gosh. Couldn't I just done that in the beginning? Well, yes, but it might have been all opposite signs too. In the end, what we did was we threw the 24 over here as a minus. But couldn't we have also thrown all of this on the other side? Yeah, those were my two choices as it turns out. But if I had chose the other one, my final answer would be off by a factor of -1. That's why we had to figure out what it was first. Also, I needed to do this for the purpose of partial derivatives. You can't take partial derivatives of an equation. You can only take partial derivatives of a function. Sometimes we make that mistake. There are no derivatives of equations, only derivatives of functions. So at this point here, I'm going to erase this. We agreed that the normal was pointing above the xy plane. So the gradient of g is 4, 8, 1. The magnitude of the gradient of g is then, what's this? 16 plus 64 plus 1 is root 81, or just 9. So therefore, my normal vector is 1/9 times this. Yes, I can multiply the 1/9 in, but it's gonna, if I do everything right, it should cancel in the next part of the problem. So that is my normal vector. That's it. I have to calculate the normal. It's its own thing. Because that's what's actually going right here at some point. Now let's do the surface area parameter. All this stuff here. So going back to here, ds is fx squared, so that would be -4 squared, plus fy squared, that would be -8 squared, plus 1 dA. Okay, formally this is the surface area parameter. This is what the second half of the integral is going to look like. But isn't that just going to be 9? So if I had asked you to find the surface area, that would be your integrand, 9 dA. If I asked you to do a surface integral and I gave you a density, you'd take your density and you'd multiply by 9 and integrate with respect to A. I'm asking you to calculate the flux. I'm asking you to do f dot n, and then whatever you get, multiply by 9 and integrate it with respect to A. That's what I'm asking you. It's just the beautiful thing is, this is the normal vector. So now, before I write the integral, I want to write, what is f dot n ds. Well, f dotted with n would be what? It's going to be 4y times 4, that's 16y. So I'm going to put 1/9 times 16y. 6 times 8. 2z times 1. And then it's going to be multiplied by 9 d8. This is ultimately going to become my integrand. Everybody cool with that? Now, the reason I did not multiply this 1/9 in is because I know eventually if I do everything right, this is what's going to happen. But again, the unit normal vector has nothing to do with the other side, right? So this is all I got left. So now I can say the double integral over the surface of f dotted with n dA is equal to the double integral over the region in the xy plane of 16y plus 48 plus, oops, wait a minute. I can't write 2z, can I? I have a double integral, can't have 3 variables. So what do I do, bud?
Plug in the equation.
Now again, this is part of the reason why you solved for z. Oh, because I need to do this. So way back here, see I haven't integrated anything yet. I'm going to make this 2 times what? 2 times 24 minus 4x minus 8y. So let me remove this because I don't want to write a double integral with a z in it and then undo it because that's bad form. I shouldn't have 3 variables in my double integral. This is where I correct everything's right here. So I have 16y plus 48 plus 48 minus 8x minus 16y. And what does that give us at this point? If I did this right, what do we have at this point?
96 minus 8.
96 minus 8x. And then the other stuff? Wow, that made this even easier, didn't it? Wow, that's not bad. Now, the reason we like to write our integrals in this kind of ambiguous form is now we decide how do we want to integrate. Do we want to integrate rectangular? Do we want to integrate polar? This is not spherical or cylindrical because it's only a double integral. Well, what's my region in the xy plane going to look like?
Triangle.
It's a triangle. I'm pretty much sticking xy, aren't I? I'm not going to go polar on this one. Could you? Yes, but it'd be really messy. It'd be really difficult. So no, we're going to go simple rectangular coordinates. So now I need to draw the picture in the xy plane. Otherwise, determining my limits of integration might be a little bit sticky. So, how do I determine in the xy plane? We'll go back to your original 4x plus 8y plus z equals 24. In the xy plane, z equals 0. So that means in the xy plane, it's just 4x plus 8y equals 24. So I have that, just that little simple triangle. Do you want to integrate it with respect to x or with respect to y? This choice should, by the way, it does not matter. But if I want to make the problem easier on myself, and by the way, it does not matter, it truly does not matter. But because my integrand has an x in it, if I integrate with respect to x first, then I'm going to have an x squared, and then I put the limits of y, and then I got to square it, and it can get a little bit messy. Agreed? But if I integrate with respect to y first, then I just get a y, and I put my limits. It makes no difference. If this were x to a larger power, then it's a no-brainer. You absolutely would go y first. You don't want to be raising a polynomial to a large power. But it's only x to the first power. So it's really not going to make any difference in terms of the difficulty of the problem. But I'm pointing it out that sometimes you have to use that in your strategy, just saying, algebraically, what would be easier? So let's suppose you want to go this way. Okay? then that means that I'm going to write 4x equals 24 minus 8y, so x equals 6 minus 2y. By the way, if I solve for y, that's just as easy, but then I'd also have fractions. So it's another reason maybe I want to go this route. Okay? I know we like to avoid fractions like the plague. So x will go from x equals 0 to x equals 6 minus 2y. My integrand 96 minus 8x dx dy. No, I'm sorry, I said, my bad. I said dy dx. I'm going to go ahead and go dy dx. Or, I'm sorry, dx dy. Because I already started that way. What is x going to range from? There, and y is going to range from 0 to 3. I'm going to show you in this case it won't make that much difference because I'm only going to be squaring it. Some of you would go this way because you avoid fractions. The other way, you have fractions, but then you only have a y. Like I said, in the long run, exactly the same amount of work, really, because it's relatively simple region. So 96x minus 4x squared from 0 to 6 minus 2y dy. I'm going to move over this way. So I have 0 to 3 of, where are we? 96 times 6 minus 2y minus 4 times 6 minus 2y squared. Again, the only reason why you might have wanted to go in different order, just a little bit of algebra here. So that's 36 minus 24y plus 4y squared within there. So what do we got here? So what, 576 minus 192y minus 144 plus 96y minus 16y squared. And in the end, it's at 432 minus 96y minus 16y squared. And get out your calculators. So we have 432y minus 48y squared minus 16/3 y cubed from 0 to 3. Now what do we get? $720?
Yeah.
Now, if we did it in units, this would be volume per area. Now, what units are those? I don't know. Cubic centimeters, cubic meters, whatever the units were for the problem. But this represents the flow of liquid, probably water. Okay? So the number in itself, there's definitely units attached. I don't want you guys to worry about the units, but do understand this isn't a work answer. Okay, it's not the same thing exactly. That's not what we were calculating here. Was this problem difficult? Shouldn't have been. I mean, it wasn't too bad. All right, let's do another one, a little more complicated. Any question on this? This is very algebraic. This is not conceptually hard to do. Once you understand what you're finding, all the problems kind of look the same. You're just hoping that you don't have a complicated force vector. But the beauty is the algebra on these problems often works so nicely. No matter how ugly the situation is, because of the way things combine, and in a lot of cases, like here, cancel. Okay, let's try another one. Let's do, sorry, I have another example here. Oh, sure. 100, not So what is my surface in words?
Hemisphere.
Top half of a hemisphere. A hemisphere, so a sphere centered at the origin, that makes it way, way simpler. A sphere of radius 10 centered at the origin. Okay, so, boom, one of those Bosu balls. Okay? What direction is my normal vector pointing? Up or down? Up. If I had said bottom half, easy to conceptualize, but it also makes it a little more complicated. Now, you really don't want to solve for z. You really want to solve for z squared, but you can't. Won't get the same answer. You got to solve for z. Okay, so I need f of xy. Remember, this is a function. The top half of the sphere is a function. The sphere itself is not a function. Okay, the top half is. So this is my z, so that's going to be the square root of 100 minus x squared minus y squared. No way around that. So I got to take partial derivatives of that thing. Okay? Now, we're going to redefine, or define, I should say, a function of 3 variables. So which way? Z minus square root or square root minus z?
Z minus square root.
Z minus the square root. Okay, now these are independent. I need this for 2 different things. I need this to figure out the surface area parameter, and then when I actually do my integration, do I need to substitute z to get z out of the problem? This I need to actually calculate the normal vector, because f dot n is a thing. F dot n is the actual integrand that I'm going to integrate. Okay, so let's do the gradient first. The gradient of g is, so in this case here, think of this as 100 minus x squared minus y squared to the 1/2. So gx is negative 1/2 100 minus x squared minus y squared to the negative 1/2 times negative 2x. And what does that give us? That gives us x over the square root. Aha. So it's positive, so that's going to be x over the square root. Now, can I be lazy? Is the partial with respect to y going to look basically the same? Yeah. That's one of the things we like about this type of shape, is that I don't have to do everything twice. I can use prior results and then comma positive 1, because of the way we subtract it. But it's important that I have the signs in front of the x and the y correct. If I mess up those signs, largely because maybe a chain rule factor, something got wonky, if these signs, if I messed up, this is going to radically change the entire answer to the problem. So you've got to be careful there. That's my gradient. So now, what is the magnitude of my gradient? Well, this squared, oops, plus this squared plus 1 all under the root. This is better or worse? Well, can I replace 1 with 100 minus x squared minus y squared over 100? Can I do that? And if I do that, what happens to the numerator? Well, the x squared and y squared cancel. So this ends up being square root of the square root of 100 over 100 minus x squared minus y squared, or simply 10 over the square root. Okay? So now I can say the normal vector is going to be the reciprocal of this times this. Now, if I actually multiply that out, it comes out sort of nice, but I'm not going to multiply it out. Now we need to do the surface area parameter. So, fx, we've just done something similar to this. when I take the partial with respect to x, that is definitely going to be negative. That's going to be negative x over the square root of 100 minus x squared minus y squared. Fy is going to be negative y over the square root of 100 minus x squared minus y squared. And therefore, ds is going to be the square of this plus the square of this plus 1 dA. Well, we just did something like this, so that's going to be 10 over the square root dA. Kind of fast forward it because we had just done a lot of that algebra already. Now, we've done all of the setup. We still don't even have an integrand yet. But what are we going to do? We're going to take this vector dotted with this vector times the reciprocal of this and then multiplied by this integrated with respect to it. And if all works out nicely, I should have some nasty stuff canceling there. And you say, well, again, why did I have to do all this? Because the normal vector is its own answer to questions, okay? Sometimes you're going to find the normal vector as, in the next thing we're going to do, the normal vector sits alone, independent of the ds part. So we still had to find the normal vector, which is the reciprocal of this times this. I don't necessarily have to multiply it through, but I do need to state it correctly. So finally, when we do f dotted with n ds, all right, there's my f, and look at your gradient function. When I multiply those, what am I going to get? I'm going to get 5x over the square root and then, hold on, did I write that correctly? Hold on one second. X, yeah, I did write that correctly. And then 5y times that guy, so plus 5y squared. And then 5z times 1. And that all looks correct. All of this multiplied, and then by I'd have the square root over 10. So the reciprocal of this times this dotted with f, and then that. Did I do something?
5x squared, right?
Oh, yes, thank you, both. 5x, did I not write 5x? Thank you, 5x squared. This looks really messy, but this stuff cancels. And again, your unit normal is the reciprocal of this times this. That's its own vector. That stands alone because we're also going to use that to answer the next question. Okay? Has everybody got that? The unit normal is its own thing. Now, I'm almost ready to write my integration, but I got a z there. So what am I going to do? I'm going to replace z with this. So this is now, how about if I write these guys together? Plus 5 times, all right, I've got all of this dA. If I multiply by root over root, will I be able to add these? Can you see that? If I multiply this by the root over the root, then I'll have the same denominator, but now I'll have 5 times the quantity, 100 minus x squared minus y squared, which will cancel with these guys and just leave me with the 500. Do we all see that? That's not the worst thing ever. So finally, boy, we filled up a lot of board just to get to this point in the problem. Okay? Okay. Everybody got it? That's where we are now. We did all of this to get to here. And we did have to swap out this z because otherwise we wouldn't be able to express this as a double integral. Because the double integral can only have two variables. Sometimes we get in trouble when we're doing polar substitution, so people will forget to swap everything. So I'll see integrals with x, y, r, and theta all at the same time. Can't do that. Now, what is my region in the xy plane? In the xy plane, what is my region? This is real easy.
Circle.
It's x squared plus y squared equals 100, isn't it? It's the circle of radius 10 centered at the origin. Well, based on that alone, I probably want to go polar, but also looking at my integrand, that denominator is kind of scary looking, isn't it? So if I go polar, what are my r limits? 0 to 10, because we just said a circle of radius 10. This is going to be 500. Now, I can replace x with r cos, and I can replace y with r sine, and then do all my manipulation, or I can just notice that that's 100 minus the quantity x squared plus y squared. That's probably easier, isn't it? So then what's this?
100 minus r squared.
100 minus r squared, which, by the way, if there's nothing additional, that's just a simple, that's a simple Calc 1 integration. That would be inverse what? Starts with an S, ends with a 9. Good, inverse sine, yeah. But there is an R, isn't there? So that's not an inverse sine, that's a straight U sub. Okay, so let's do that as a U sub. Let me erase a little bit of this off to the side. Because the way that looks, it looks kind of scary right now. So what I would do first of all is I would rewrite this as 500 times 100 minus r squared to the -1/2. Ah, okay. That would make it easier. So now, let's do this off to the side. If I let u equal 100 minus r squared, then what's my du?
2r.
Negative 2r dr. Well, I don't quite have that. So I will I'll put the -2 and then outside the -1/2. Okay, so now what have I got? What does that now become? I have 500 u to the 1/2 du. So when I do this integration, 500 u to the -1/2. What's the antiderivative of that? Times how about 1,000? Yeah. Everybody cool with that? Okay, so this becomes, you just said 1,000 u to the 1/2. That's my u to the 1/2. Evaluated from 0 to 10 d theta. But I got a negative in front. That's okay. When I evaluate at 10, what do I get?
0.
0. Ah, when I evaluate at 0, I get square root of 100, which is just 10. Anybody see that? So I get 0 minus 1,000 times 10. Can I answer the question straight up now?
Yeah.
What's the answer?
10,000 pi.
10,000 pi. That's a lot of pi's. That's it. Now, the integration itself shouldn't have troubled us because we've been doing this integration. And I mean, literally, when you got to here, that should feel very comfortable because you've done that problem a million times at this point. It's getting to that point is the trick, isn't it? It's not the answer, it's getting to that stage where you could actually integrate it. So, if I have the integral of f dot n ds, I'm calculating the flux. So the easiest way to think of this, again, is this idea that I'm creating kind of a dam with a sheet. But it could also be that I put something porous in the river itself. In a fixed, not letting it flow down the river. I have something fixed in the river itself and the water is flowing through that fixed object. Okay? So it's really the same idea. So this is what flux measures. Any question on this? And again, is this something you use in math in the future? No, pure physics. You use this stuff in the physics. But we have to do the math because they're not going to teach you this part in the physics class. They want to know that you can do the calculation. Now, the last thing we're going to do essentially the three-dimensional version of Green's theorem. I had mentioned this to you last week, or last time. Because Green's theorem, as awesome as it is, only applies in 2 dimensions. So, I'm moving through space on a curve, and at every point I'm applying a certain amount of force. I can ask you to calculate the total work done. That's what a line integral is. That's the quiz you just turned in. Your first question was exactly that. You were moving in three dimensions. I gave you a very specific path, and I gave you a very specific three-dimensional force, and you calculated the work. That wasn't all that complicated. But could it have been complicated? It could have been very complicated. So imagine I'm doing the same problem, but I have a closed loop. But not on the XY plane. I have a closed loop in 3D. It seems like we ought to be able to figure out a way to apply Green's theorem to that problem. I mean, it seems like we should. Problem is, Green's theorem very specifically was only 2-dimensional, and the way we set it up, right? Only a dx and a dy involved. There was an my and an nx, and, but let's play with it a little bit and let's tweak it, okay? So, I'm going to go over some of the things we already know, all right? I've got 2-dimensional force. Remember, it's m of xy, n of xy, over path c, okay? We know this. So then, the work done, okay, this goes back to sort of the beginning of line integrals. We now know that is the work done, but there were alternate ways to write it. We also said it could be written this way. Isn't this the quiz you just turned in? You parameterized, you said, oh, let me make all my functions functions of t. And then I did dr dt integrated with respect to t. That's this. But I also showed you another way. We could also think of it as f dot ds. And this is a little, I'm sorry, f dot, not ds, sorry, f dot t ds. And this is little s. This is the arc length s, not the surface s. Big S always refers to the surface, little s always refers to the arc length, and they have nothing to do with each other except that they are the same letter of the alphabet. Okay. I know all three of these things are the same. This is one way of doing it, and when I gave you the problem in this form and I gave you the curve, you probably parameterized it because it made the problem easier to do. But when you parameterize it, you are essentially doing this problem without realizing it. Okay? But this problem is also fair game, and that's actually the one we're going to concentrate on. Okay? So now what if C is closed? Then what happens? Then all of this becomes basically, I'm just going to, if C is closed, then I go like this. All right. Now why is that important? Because the first one is straight up Green's theorem. Okay? I know now the answer is the double integral over the region in the xy plane of the partial of n with respect to x minus the partial of m with respect to y. Okay, this was the last lecture we did before the break. This is ginormous in terms of its importance and its use. Okay? But this is very strictly two-dimensional force. I live entirely in the xy plane, nothing else going on here. So now, let's change something a little bit. When I'm walking around this room, am I moving in 3 dimensions? Well, yes, because we live in 3D. But if you charted my motion, isn't my motion entirely on the xy plane, even though I am in 3D? So if you gave me a vector path, an r of t, wouldn't it be of the form x of t, comma y of t, comma 0? How do you know? Because I'm not going up and down. Do you all agree that my z motion is 0 the entire time I'm moving? Right? Last time I checked, my feet are pretty much staying on the floor. I'm not doing a lot of jumping. Okay, so everybody cool with that? So what if we had something where the force was this? Now, we're not cheating. There are textbooks that actually cheat. There are textbooks that will say, well, we consider all two-dimensional motion as the same thing as three-dimensional. No, you can't. Nope, when you're looking at your TV screen, it is entirely two-dimensional. Sorry, you can't look at it as three-dimensional. No, you can't do that. I can take 3D and project it onto 2D, but I can't make 2D into 3D. But what if I am in 3D, but I have 0 in the z direction, like I just described? There's nothing wrong with this concept. When you're walking around, you're probably doing this, aren't you? But what's the difference now? Now it's m of x, y, and z, n of x, y, and z, comma 0. Okay? No big deal. I am moving in this manner, but let's suppose my motion is entirely on the xy plane. I keep losing my pins here. So my curve, right, this curve is entirely on the xy plane. Okay? Now, when I do this, my curve is entirely on the xy plane. What direction is my normal vector?
Oh,
So, be more specific.
it's perpendicular.
In what direction? Pick a letter of the alphabet.
Z.
Z. Okay, good. Everybody's giving me this. Do you all agree that my normal vector at every point is in the z direction? No question. Okay. Is that important? Yeah. In fact, I'm going to be very specific. And let's just say, for argument's sake, we're pointing up as opposed to down. In the long run, that's not going to be an issue. Would you agree that my normal is 0, 0, 1 then? Okay. That was really a stretch. So, this is my force. I'd like to calculate the curl. We've never actually used the curl to answer a question until today. Can you tell me the curl of this? Yeah. Let's do it easy way. So my curl is 0 minus 0, 0 minus 0, oh, that's pretty exciting. And obviously 0 again, no. Nx minus my. Huh. Okay, you with me? You're laughing. Why are you laughing? Do you see something coming? You can see something coming. You're 3 chess moves ahead. You see something that lives in Greenstone, but I have a vector. I don't want a vector. What if I do this? Remember I said you always calculate n independent of the surface and everything else. What is this exactly?
Okay, that's close enough.
Huh. This is interesting. because I am in 3 dimensions, but my motion lived entirely on the xy plane and I had a closed loop. I cannot use Green's theorem because I live in 3 dimensions. But shouldn't the answer to the question act like Green's theorem in a sense? Yeah, but we're actually going to do this to do our calculation. By the way, those 3 integrals with the loops around them, these 3 integrals with the loops around them, well, particularly these 2, let's say, is there an indication what dimension I'm in? This one looks 2-dimensional, but what if I have a z component of 0? Then all 3 of those technically could be 3-dimensional, couldn't they? Does everybody see that they could all be 3-dimensional? Because I didn't say what the c was. Now think, I'm in 3D, I'm just stuck on the xy plane. So why is that kind of cool? Because now when I do this, what am I getting? I'm actually getting this. Because we know that the integral I produce should look just like the Green's theorem integral, because when I'm doing this whole thing, so, well, is that important? Well, in this case, because it ends up being I mean, we know, well, sorry, let me make sure. Curl of f dot, oh, I wrote d, sorry. This should be dA, not ds. I'm in the xy plane there. This is Green's theorem, but I'm in 3D. Well, okay, I'm cheating a little bit, but I'm in 3D, but my entire motion was on the xy plane. Okay, great. Can we tweak this a bit? Yeah, I'm going to tweak this a whole bunch. Because this quantity right here, we derived Green's theorem. I did a whole lot of work last day. I used all the boards up. We derived this as a 2-dimensional problem. But I just said if we consider our 2-dimensional motion in a 3-dimensional world, then this quantity was exactly the same as the curl of f dotted with n. Because my n was pointing in the z direction. And the curl we just did was just this. Okay, you with me on that? So here's what I want to do. What's wrong with me taking my world and tilting it? If I said, what's the work? Draw me a big loop on the floor. And you're going to do your work. Now, if I tilt the world, your loop is going to look different, but it's still on the floor. I'm just tilting the world. Shouldn't I be able to use the same reasoning to calculate the answer? Here's what I mean. I now have a loop. Make sure I get my picture correct. I now have a loop, let's say it's going tilted. This is not on the xy plane. It's now doing this through space. Okay? And let's say, there's my normal vector now. I just took this and I did this. But don't we do things where, like, think of rotation of axes with conics. Don't I do things and I just reorient it from this new coordinate system in a sense? So if I thought of this, well, I still am on a closed loop, so shouldn't I still be able to use this? Because this had nothing to do with me being on the xy plane. This was a result that I saw because I started on the xy plane. But what if I tilt it? Now the difference is, because this was already on the xy plane, this was a dA because this was an r of xy to begin with. Now what if I do this and I ask you to do, make sure I got it. Oh, sorry, I'm going to do I'm doing the TDS one. Little s. I know when I did it for this problem right here, I already knew that this was going to be the answer. But the answer we actually said come from here. So now I want to make my loop different. There's nothing in this that says what plane I'm on. It just says I have a closed loop and I'm integrating over that. Turns out, now I'm going to put over the surface because I'm not on the xy plane. I have to project onto the xy plane, right? Eventually. But of what? Of the curl of f dotted with n ds. Now the reason it's ds, again, is because I don't live on the xy plane. I have to project onto the xy plane just like we did with the surface integral. And what we have here is basically the three-dimensional analogy to Green's theorem. And the key was going way back to here and saying, let's consider three-dimensional motion, but all on the xy plane. We still get the same things. But I use the curl and the normal to get me there. So now if I simply tilt, and now my loop is going like this, I couldn't do that last state, because last state I needed it to be purely two-dimensional in order to pull this off. Because what were we doing? We were doing an area in the xy plane. This isn't necessarily a simple area in the xy plane like I did last day, but when we do the ds and we project it, right, then we do the arc length parameter just like before. I mean, not the surface area parameter just like before. This, and by the way, this is work. This is called Stokes' theorem. Okay? It's the three-dimensional analogy to Green's theorem. And it's really cool that we could do this. Now, is this hard? It's relative. Again, it always depends how complicated is your force and how complicated is your region. I can't say it's easy, I can't say it's hard. But let's do an example of one, shall we? Told you we had a lot of stuff to get through today. Now, there's sometimes confusion because the way you do the flux problem is you're integrating a dot product, right, over a surface. You're doing the same thing here, but you're not doing f dotted with n, you're doing the curl of f dotted with n. So you will always get a very, very different answer. Okay? Now, this one very specifically is a work answer. Okay? That's, again, it's the three-dimensional analogy to Green's theorem, which is a work problem. So, let's do an F and the surface will be we'll do a simple plane, we'll do like a similar to what we did before. The first octant portion. So essentially what we're doing is, I'll draw this picture because it's important that we understand what we're about to find here. Okay, everybody see this? This is what we have here. I'm cutting, again, with a plane. But what we're actually going to do is the surface here is this triangle. But if I think of this as a loop, my loop is actually the edges of that triangle. Does that make sense? So ultimately, when I integrate, what's my region going to be that I integrate over? Anybody want to tell me? It'll be the triangle that's sitting in the xy plane ultimately. Because ultimately I got to project this onto the xy plane. Now what's crazy about Stokes' theorem, one of the things about Stokes' theorem that's interesting, it really doesn't even matter what the surface looks like. For example, if we were dealing with the top half of a hemisphere, it would only be the circle part. It doesn't matter how high the hemisphere goes. It doesn't matter if it's a paraboloid. It's not the surface, it's the rim of the surface. Because that's what I'm actually... So ultimately, it's the path that you're taking. It's less about the surface, it's about the rim. Think of it like that. And that does kind of defy things at first, but then when you do the problems, you'll see that that shows up. So what do I need to do here? Well, I need a normal vector. So, again, are my normals pointing upwards or downwards? Upwards. So we will let, I need to do two things. Let's start with our normal. So, heck, I can just do all of this. So g of x, y, z will be 3x plus 2y plus z minus 6. Why? Because I want to keep the coefficient of z positive. So that made it really easy. Okay? All right, so now the gradient of g would be 3, 2, 1. The magnitude of the gradient of g will be 3 squared plus 2 squared plus 1 squared under the root, or root 14. So therefore, my normal vector is 1 over root 14 times 3, 2, 1. Yes, it is absolutely correct to multiply it out, but we expect there to be some canceling down the road. Now I need to figure out my ds, my surface area parameter. So going back to that, I'm going to define f of xy to equal z, which will then be 6 minus 3x minus 2y. Now, why do I need to do this? Well, I have two things. I need my surface area parameter, and I need my region in the xy plane that I'm going to integrate over. So I actually have to do this. Again, this is independent of that stuff over there. They have nothing to do with each other during the process, but it all comes together beautifully in the end, I hope. Okay, so if I got this, then my surface area parameter is the partial with respect to x squared plus the partial with respect to y squared plus 1 squared. dA, which is, of course, if I did it correctly, root 14 dA. But I also needed the correct signs over here. Now I need to do the curl. Before I do the dot product, I've got to do the curl. All this stuff. Okay, so going all the way back to here, so I don't have to rewrite it. Hopefully you guys take my lazy shortcut tricks that I show you and actually apply them and don't make it complicated. I still see people setting up determinants, which makes me laugh because I'm a linear algebra expert. You would never take a determinant in any capacity to do a cross product. Will you get the right answer? Sometimes. Do you know what the upper limit is in this class? 50%. Because everything we do incorrectly. Now never do a determinant because you make it 10 times longer to be right at best half the time. You say, well, I'm always right. No, actually, as a group, we're incorrect far more often than 50% of the time. It's actually not that close to 50. You'd think it'd be 50, but it isn't. It's actually a lot less. He said, but I did it in physics. Yeah, but we do it incorrect in physics too. So don't make it complicated. Make it really, really simple. In other words, there's no linear algebra whatsoever in cross product. So the curl of f is 8y minus 0, 6z minus 0, 36x minus 0. Does that look right? Didn't make it, no mistakes there, I hope? I'm a big fan of not making mistakes. Now, at some point in the process, whether I do it now or I do it later, at some point in the process, I need to swap out the z. Because remember, we're doing a double integral, so I can't have the z. In reality, if you found it easier to project onto the yz or the xz planes, there's nothing wrong with that. But yet, generally speaking, we've been using floor and ceiling this way, just because conceptually it's easier. In real life, when you're doing this problem, you set it up however you want. You're always going to set it up that way, because it's easier for you to conceptualize. But there would have been nothing wrong with me changing the surface. I just don't like doing it that way because then you think every problem is having 3 sets of equations when it really isn't. So that's the curl of f. I'm going to replace the z now. Later, the other problems I did it later, I'm going to show you can replace it at any point. So where did I define z? Hold on. Oh, so, over there. So I'm going to replace the z with 6 times that quantity. It actually doesn't matter when you do it. I'm just going to show you. You could also do it this way if you chose. A lot of times you'll choose to wait till the end, just less writing perhaps. Now, I need to do the curl dotted with n ds. So when I do the curl dotted with n, ignore the coefficient, what do we get? Let's do this. So I'm going to get 3 times, I'll just write it up, 3 times 8y plus 2 times 36 minus 18y minus 12y. Is that correct? And then plus 1 times 36x times 1 over root 14 times root 14 dA. Did I do something?
18x, I think, what?
Oh, thank you, Bob. That's an 18x. All right, good. Does that look right so far? Okay, so what have I got inside here? I've got 24y plus 72 minus 36x minus 24y plus 36x. Let's see, does anything cancel? Oh, that's an x. Looking to me like most everything canceled, didn't it? Is that a good thing? Well, it's a thing. Good or bad, that's what I got. So this becomes what? 72 dA. Woo! Like that. Now, I mentioned before, a lot of times everything works out nicely because of the fact that the way you're combining things, and because some things are getting used more than once in a sense. So Stokes' theorem says that original problem is just going to be the integral of 72 dA. Wow. Okay, what is the region in the xy plane?
Triangle.
Very specifically, what triangle? If I replace z with 0, then it'd be 3x plus 2y equals 6. Agreed? So, I'm going what? My region in the xy plane is a simple geometric shape. I'm integrating that area with a constant integrand. By the way, what is the area of this triangle?
3.
Yeah, 1/2 base times height. Do you all agree the area is 3? We're done. Wait a minute, can you do that? Why? Because my region was a simple geometric shape that we already knew the area of, and my integrand was a constant. This would be the equivalent of saying I have a triangle in the xy plane, and it's 72 units high across the board. So think of z equals 72. So I have a triangle in the xy plane, and it's 72 units high. What is the volume of that 3-dimensional solid? But isn't that just a simple prism? Because all my boundaries think of as constants. Can I do this? Yeah. Can I go ahead and do the entire integration? Of course. When your region in the xy plane, let's say the region was a circle. Could I take the area of the circle and multiply by 72? Yes. What if there's a variable here? Then can I do this? No. He could only do it because the integrand was constant. So when we're at the last step of an integration, and we have the constant limits, the 0 to 2 pi, or whatever, the last limits are constants, and my integrand's a constant, you already know you can take your integrand and multiply it by the length. You already know that because that means technically you were finding the area of a rectangle. What we're really doing is finding the volume of a prism in this case. You can think of it that way. But if there's a variable in the integrand, no, there's no shortcut. You do have to do the integration. I love shortcuts when they exist, but you have to know when they exist. When everything is constant, there's usually a shortcut. Okay? Any questions? Okay, so Stokes' theorem, you see curl of f. That's how you know it's Stokes' theorem. It doesn't look like anything else in terms of how you do the problem because you have to do the curl. So now we finally have use of a curl. Now, what is the curl exactly? This is kind of tricky. Okay, how many in your physics classes have you ever done anything with rotational stuff? Did you ever use the term curl? The simplest one I like is like a paddle wheel. The old riverboats. You have the paddle wheel, and you're actually calculating a form of work in that sense. If you're thinking of it like that, or you can have a closed objects and just like a blender kind of thing, as long as it's going circular. That's why it's called curl, because it often is related to circular motion. This isn't circular motion, but I did go around a loop. So that's the concept of curl. But you're doing a calculation, but it's different because, again, it's like a Green's theorem problem because you're only looking at the loop that you're traveling. Even though you're in 3D, you're still only looking at the loop you're traveling. So now let's go way back. Okay, I have my wheelbarrow, and I want you to go all the way around the campus, right? And stuff is leaking, it's falling out, and that's what the line integral was. What was the work done from point A to point B with this variable force? But then I said, okay, I fixed up my wheelbarrow, I patched all the holes, I put a dome cover, kind of like on the back of your truck, you put a shell. I put a shell, so now nothing is escaping and nothing is being added on. So I made it so that my force. Yeah, I have to apply force in different directions, but maybe my force isn't changing, only the direction's changing. Okay, so going from point A to point B maybe got a lot easier. Now what if in fact, I'm making my force conservative, in other words. What if now I did the closed loop? You said closed loop conservative force, I know that's going to be 0, but did we do that problem in general? No, I didn't give you that problem. I gave you from point A to point B. The quiz you just turned in. I gave you a problem from point A to point B. What if I said, and now come back? I'm now giving you a closed loop, correct? Could we use Stokes' theorem on that problem? Because it's a closed loop.
I don't think so, because it doesn't have a region to area.
Well, it kind of does. It kind of does. Because the x, y, and now it's not, and say it was easy, but we would have to be really clever to figure out what that looks like, right, on the xy plane. But if we did it on the xy plane, x was equal to 4t and y was equal to 2t squared. That's just a parabola on the xy plane. Oh, so I want you to just keep your imagination going, because I'd like you guys to think about if you did this. So I'm moving in 3D, and I said go from point A to point B and give me the work done. And that was not a difficult problem. But what if I had asked you to come back as a closed loop? Do you think the answer would be 0? Well, do you think it's a conservative force? Probably not a conservative force. So if it's not a conservative force, the answer is not 0. Think of Green's theorem. Weren't all the Green's theorems closed loops? Yeah. Did you get 0 for all your answers? No. Rarely do you ever get 0. Oh, when do I get 0? When it's a conservative function. But I can be conservative in 3 dimensions. I'm hoping this is really obvious. I just did a closed loop and you have a conservative function. Folks, if f is conservative, tell me about curl of f. Isn't it the 0 vector? Isn't that how we determine whether a 3-dimensional force is conservative? Oh yeah. The only way you can determine if it's conservative is to actually find the curl. Oh, okay, so if I find the curl, and the curl is the 0 vector, then I know it was a conservative force. Oh, and by the way, Stokes' theorem, which is a closed loop in 3D, would now give me 0. But that's consistent, isn't it, with everything we did? So I want to consider this problem here. This is not an additional problem. I just want to see if we can apply something we did today. So my force was y, z, x. Okay? Can we find the curl of this? Because before you started, nobody was thinking conservative force here. So what is the curl of F? So 0 minus 1, 0 minus 1, 0 minus 1. Is this a conservative force? No, because that's not the zero vector. Okay. So if I wanted to do this problem, I'm going to go curl of F dotted with n. But the curl vector is pretty easy, though. So if I wanted to make this a closed loop, would this be a difficult problem? Probably not, because that was really friendly. Why are curl vectors typically friendlier? Same reason gradient vectors are typically friendlier. What's a gradient vector? A vector of partial derivatives. Oh, what's the curl vector? It is a vector technically of partial derivatives, isn't it? So often it's a simpler vector in that sense. So sometimes we forget that. Now, I wouldn't call this complicated by any stretch. But what do you notice about the curl? Smaller degrees on everything, isn't it? Not larger degrees. That's far more common than not. Okay? So, interesting problem. We have one thing left. So what we're going to do next day is one of the more complicated setups, but not a difficult problem to do. What is flux? Okay? Flux is, think of a surface, and I'm asking for the water flowing through the surface. So could I put, like a parachute? Think of a parachute in the water. But now you have a parachute submerged in the water. Is water going to flow through it? Sure. There's nothing wrong with that. What if I put a three-dimensional closed object in the water? That's not a surface. At the very minimum, it's two surfaces, right? That's why a closed loop at the very minimum is two different loops. That's what we did when we derived Green's theorem. I said, let's look at the simplest case, two different loops. But can't we have a closed loop that has, we can go around a box, we go around an octagon, right? Now there's 8 different curves. But a closed loop has to have at least 2 curves. Well, a closed surface, think of the simplest one, a sphere. You have 2 surfaces, don't you? You have a top and a bottom. What if I wanted the flux? So I put a porous ball in the water. So the water actually can pass through the thing, okay? Wouldn't I have to calculate the flux for each piece? Yeah. What if I put a box in the, oh my God, now I have to, a simple box. Doesn't the box have 6 faces? That means I'd have to do 6 different fluxes. No way around it. Put a soccer ball that's slightly deflated so now you can actually see the little hexagons, right? Those are called tessellations. I'd have quite a few surfaces, do you agree? And if I wanted to find the flux of this closed object, I actually have to calculate every single surface's flux. Okay? Why was Green's theorem a benefit? Because if I had multiple paths but I closed my loop, instead of doing the multiple paths as line integrals, I could do the closed loop over the area. So imagine now I want to find flux over multiple surfaces. That would be a gnarly problem. That would be very long. Well, what we're going to do next day is the shortcut. Kind of like what Green's theorem was to a closed loop, we're going to do what would be for a closed surface. Now, I want you to think logically. If Green's theorem took my closed line integral and said, let's do a double integral over the area, well, my flux right now is a double integral over the surface. What do you think it might turn into? Triple integral over the volume. That's exactly what it's going to be. And it turns out it takes Arguably the most difficult problem you could run into at this point would be find the flux of a closed surface, because you'd have to do so many problems. And think about it, each time you did a problem, you got to start from scratch. New normal vectors, new surface area parameters, and you'd add them all up at the end. Yikes. But if I could do one thing, that thing may not be easy, but it's only one thing. Green's theorem we saw generally made things easier though, right? Because I was dealing with partial derivatives. So the last thing we're going to look at is, it's not Green's theorem, it's sort of the three-dimensional analogy of Green's theorem, where closed loop, closed surface. And it's really cool, you'll love that. And that is literally the end of the course. So we will also be reviewing next day. So I do want to remind you, I posted the practice test like, last semester I think it was, or something. It's been a while. Make sure you look at it if you haven't already, because we have a test next Monday, but our review is going to be taking place during Wednesday. And it's a shame to show up for a review not having actually looked at the material, right, that the test is on. So we finished the test material the last day before the break. So we have material today and Wednesday. That's on the final, and that's what your last two quizzes are. So when you walk into the final, there will have been 25 lectures and 25 quizzes. The first 23 lectures were also on exams. The last two lectures aren't, but you will at least have quizzes on them. So there's nothing on the final exam that you will not have at least been quizzed on, okay? I don't do that. I know people do, but they're just really mean people that do that, Let me throw a final at you with no question you've ever seen before. That's probably not going to be a good final. All right? We good? Okay, let's go ahead and stop that. You got